problem 5 is another problem where we're comparing the use of energy methods, the work-energy theorem, and the use of old-fashioned kinematics to solve a particular problem. This is a problem where you have a frog jumping off the side of a table. So if here is our table, and our friendly frog jumps off of the side of it here, initially moving horizontally at some speed v0, its trajectory will curve down and hit the ground somewhere over here. To use the work-energy theorem again, we need to have clearly identified before and after states. So we'll call those A and B. The problem also gives us a symbol for the height of the table. That height is h. So I'm going to do this twice, once with kinematics and once with the work-energy theorem. In the kinematics approach, which I will do first, we'll put that down here below the picture. So we're answering the question, what is the magnitude of its velocity when it lands? So what I want to know, I need to find what is the magnitude of v at the time when y equals 0. Implicit in that is a choice of coordinate system. So I am choosing this point here at the bottom of the table to be my origin. And the coordinate axes I will use are upward will be y, oops, and to the right will be x. So to figure this out, I need to find the time when y equals 0. So first, to do that, I know y of t is going to be y0 plus v0 yt plus 1/2 ay t squared. Now, I know a few things here. One of them, I know that the initial velocity in y is 0. I know that the initial y position is just the height, and I know that ay is minus g. So that becomes y of t is h minus 1/2 gt squared. And if I set that equal to 0, and I solve, this gives me, oops, touchscreen glitch. This tells me that t is the square root of 2h over g. Now I need to find the velocity at that time. I need both components because I'm finding a magnitude, right? So now I need Vx and Vy at that time. Vx is just V0. Oh, that was meant to be a bullet point, not a minus sign, so we'll just do that. Since there's no acceleration in the x direction, Vy is 0 minus gt. If I plug that in, this gives me minus g times square root 2h over g, which is square root 2gh. So combining these together to finish solving the problem, I know that the magnitude of v, which is the thing I was looking for, I can get with the Pythagorean theorem. And this is going to be square root v naught squared. Let's see, vy is square root 2gh, so vy squared is just 2gh. So that is the approach using kinematics. Now, I'd like to see how to do this using work and energy. Remember, the work-energy theorem says that work done is the change in kinetic energy. So I can write the kinetic energy at A plus the work done by all forces in going from A. Let me make that a bit neater. The work done by all forces in going from A to B equals the kinetic energy at B. Now, in this case, the only force here doing work is gravity. And the work from gravity is going to be equal to, well, let's see, gravity is doing positive work because I'm moving downward. So this is going to be the force of gravity times the distance moved downward, which is just h. So in this case, this is force times delta y. So, filling in those symbols, I have 1/2 mv naught squared, because that's the velocity at A, plus the thing I just figured out, the work done by gravity is mgh, equals the kinetic energy at B, 1/2 mv final squared, or I'll write mvb squared. And now all there is to do is to solve for vb. I can cancel my m's. I can multiply through by 2. So that gives me vb squared is v naught squared plus 2gh. And then, as you might expect, vb is just the square root of all of that, of v naught squared plus 2gh, which is the same result we got before. So that was a lot easier, right? The problem, one of the hints that's given to you there is a particular bit of mathematics that you don't have to worry about when you're doing the work energy theorem. That is separate x and y components. You will need to think about what direction forces go in order to calculate the work that they do, right? We did need to think that, oh, gravity is only in the y direction, so when we're thinking about the work done by gravity, I only need the displacement in the y direction. But that actually makes the problem easier. I never needed to think about anything having to do with the x direction here. This could have been even messier in the kinematics section had I written down a formula for x of t, for instance, had I not pondered that. So you've seen this problem before, but this illustrates what you can do with the work energy theorem. Now, there are some questions you could not answer with energy methods, and this is really important to keep in mind. Questions like, how much time would it take to hit the ground? Which direction is it moving in when it hits the ground? Where does it hit the ground? None of those questions connect to energy. But the question, how much speed does it have, that connects to kinetic energy, and thus we can address it. So that is problem 5.